Hello there, and welcome. Tonight I want to take you somewhere far from the concerns of your day, far from the gentle weight of everything you carry. I want to take you on a journey across the cold, quiet darkness of space, past the orbit of our pale blue home, past the red deserts of Mars, past the tumbling rocks of the asteroid belt, to a place where storms have raged for longer than human memory can truly comprehend. So settle in, let your body find its comfortable weight against wherever you rest, and allow your breathing to slow, because tonight we're going to Jupiter, and we're going to solve a mystery that has puzzled humanity for 400 years. Perhaps you have seen it before, this giant world in photographs or illustrations, a massive sphere of swirling clouds banded in shades of cream and orange and brown. And perhaps you noticed somewhere in those bands a spot of deep crimson, an oval of rusty red that seems almost like an eye gazing back at whoever dares to look. This is the Great Red Spot, and for centuries it has kept secrets that we are only now beginning to understand. Tonight, in the quiet hours as sleep gently approaches, we will explore why this ancient storm absorbs light the way it does, why it appears as this distinctive shade of red, and what that tells us about the magnificent, mysterious universe we inhabit. It is a question that might seem simple at first, perhaps even trivial to wonder about the colour of a distant storm on a distant world. But consider this. Consider how many generations of astronomers have pointed their telescopes at Jupiter and wondered, truly wondered, what could possibly create such a persistent, such a vivid marking on the face of the largest planet in our solar system. It is a question that connects us to those early observers, to Galileo himself who first saw Jupiter's moons through his primitive telescope, to the astronomers of the 17th century who first noticed something unusual in Jupiter's southern hemisphere. When we wonder about the Great Red Spot, we join a long lineage of curious minds reaching across time, all of us looking up at the same distant world, all of us asking the same beautiful question. What if this crimson eye, this vast storm larger than our entire Earth, was trying to tell us something about the very nature of light and chemistry and time? What if the answer to why it absorbs light the way it does could unlock deeper understandings about planetary atmospheres, about the conditions on countless worlds we have yet to discover, about the way sunlight transforms the universe it touches? Tonight, we explore these possibilities together, and I invite you to let your mind drift among the clouds of Jupiter, to feel the wonder without any need for urgency, to simply be present with the mystery as it unfolds. If you love this cosmic journey, if you find yourself drawn to the gentle exploration of space's greatest mysteries, I would be so grateful if you would take a moment to like this video and subscribe to this channel. And I am curious, truly curious, where are you watching from tonight? What time is it there as you settle in for this journey to Jupiter? Leave a comment below and let me know, because there is something beautiful about knowing that people all around our small world are looking up at the same stars, wondering about the same cosmic questions, connected by curiosity even as we rest in different time zones, under different skies. Now, let us begin our approach to Jupiter, and let us start by truly appreciating the scale of what we're about to encounter. You see, Jupiter is not simply a large planet. Jupiter is a world so vast, so impossibly enormous, that our minds struggle to truly grasp its dimensions. More than 1,300 Earths could fit inside Jupiter's volume. If you could somehow stand on a solid surface at Jupiter's cloud tops and look up at its sky, you would see a horizon that curves away so gradually that it would almost appear flat, extending in every direction farther than you could possibly see. The distances involved are dreamlike, the kind of numbers that slip through our everyday understanding and into something more like poetry. And within this immense world, taking up a space that seems almost modest in proportion, but would dwarf our entire planet, spins the Great Red Spot. At its widest, this storm stretches roughly 16,000 kilometers across, though this measurement has changed over the centuries, fluctuating like the breathing of some vast cosmic creature. To put this in perspective, you could place Earth inside the Great Red Spot and still have room to spare. This is not a small weather system, not a hurricane or typhoon scaled up to planetary proportions. This is something else entirely, a storm so persistent, so stable in its instability, that it has maintained its general form for at least 350 years of continuous human observation, and possibly much, much longer. The first reliable observations of the Great Red Spot date back to the 17th century, though there is some beautiful ambiguity in the historical record. In 1665, the Italian astronomer Giovanni Cassini observed what he called a permanent spot on Jupiter, and his observations were detailed enough that many scientists believe he was looking at the same storm we see today. Imagine that for a moment. Imagine that the storm you can photograph tonight with a modest backyard telescope is the same storm that Cassini observed over 350 years ago, when the scientific revolution was just beginning to reshape human understanding, when Newton had not yet published his laws of motion, when the very concept of what a planet truly was remained shrouded in mystery. Some researchers suggest the spot may have formed even earlier, perhaps visible to observers in the early 1600s, though the records become hazier as we reach further back. There was a period in the late 18th and early 19th centuries when observations of the spot became sparse, leading some to wonder if the current Great Red Spot is the same feature Cassini observed, or a newer storm that formed in the same general region. This uncertainty does not diminish the wonder, though. If anything, it deepens it. Whether the Great Red Spot has been spinning continuously for 400 years, or whether it has regenerated once or twice in that period, the fact remains that Jupiter has maintained some form of giant anticyclonic storm in its southern hemisphere for longer than most human institutions have existed. Think about what was happening on Earth when this storm was first observed. The 30 Years' War was devastating Europe. The Ming Dynasty was falling in China. The first permanent English settlements in North America were still fragile, uncertain experiments. Slavery was expanding across the Atlantic world. The scientific method itself was still being invented and refined. And through all of this, through every war and revolution and transformation that has reshaped human civilization, the Great Red Spot has been spinning on Jupiter, indifferent to our struggles, patient in its ancient violence, keeping its secrets in shades of red. This is what I mean when I say that space has a way of putting things in perspective, not in a way that makes us feel insignificant or meaningless, but in a way that connects us to something larger than our individual moments. When you look at Jupiter through a telescope, you are performing the same act of wonder that humans have performed for centuries. You are joining a community that spans generations, a community united by curiosity and by the simple, profound desire to understand what lies beyond our small world. The Great Red Spot does not care about human history, but human history has cared very much about the Great Red Spot, and that caring, that persistent wondering, is one of the most beautiful things about our species. So here we are, approaching Jupiter in our imagination, watching as that great banded world grows larger in our mind's eye. The colours are subtle from a distance, cream and tan and hints of orange. But as we draw closer, the complexity reveals itself. Jupiter's atmosphere is arranged in alternating bands called zones and belts, lighter and darker stripes that wrap around the planet parallel to its equator. The lighter zones are regions where atmosphere is rising, cooling, and forming high clouds of ammonia ice that reflect sunlight brightly. The darker belts are regions where atmosphere is sinking, warming, and revealing deeper, more colourful cloud layers below. The whole system is in constant motion, driven by Jupiter's rapid rotation and by heat welling up from the planet's interior, a dynamic and ever-changing canvas painted on a scale that defies comprehension. And there, nestled in the southern hemisphere, in a region where the bands interact in complex and persistent ways, we find our destination. The Great Red Spot appears first as a subtle oval of colour. Then, as we approach, it reveals itself as a vast whirl of clouds, a spiral pattern that speaks of rotation and energy and the strange, beautiful physics of fluid dynamics on a giant world. The clouds within the spot are elevated above the surrounding atmosphere, rising several kilometers higher than the cloud tops nearby. This elevation is part of why the spot appears distinct, why it maintains its identity against the constant churning of Jupiter's atmosphere. It is a high-pressure system, an anticyclone, and like high-pressure systems on Earth, it rotates in a particular direction, in this case counterclockwise as viewed from above Jupiter's southern hemisphere. But the elevation and the rotation do not explain the colour. They do not explain why this particular storm, among all the storms on Jupiter, appears in this distinctive shade of red. Jupiter has other storms, other oval features that come and go, but most of them appear white or pale in comparison. The Great Red Spot is different. The Great Red Spot has always been different, and for centuries the reason why remained one of the most persistent mysteries in planetary science. You might think that determining the color of something would be straightforward, that we could simply analyze the light coming from the Great Red Spot and immediately understand what chemicals must be present to create that color. But the reality is far more complex, far more interesting, and far more elusive. Light is a messenger, yes, but it is a messenger that speaks in riddles, and decoding those riddles requires understanding not just what is present in an atmosphere, but how those substances interact with light at different wavelengths, at different temperatures, at different pressures. The Great Red Spot exists in an environment so different from anything on Earth that our intuitions about chemistry and color often lead us astray. Consider what we know about Jupiter's atmosphere. The visible cloud layers are composed primarily of ammonia ice, giving the planet its pale, creamy appearance in most regions. Below the ammonia clouds lie layers of ammonium hydrosulfide and water ice, deeper and harder to observe directly. The atmosphere itself is mostly hydrogen and helium, with trace amounts of methane, ammonia, water vapor, and various other compounds. This is not an atmosphere like Earth's, not an ocean of nitrogen and oxygen, but something more like a compressed gas giant, where the pressures and temperatures increase dramatically as you descend, where the distinction between gas and liquid eventually becomes meaningless at the depths where hydrogen transforms into a metallic fluid. In this alien environment, chemistry behaves in unfamiliar ways. Compounds that would be unstable on Earth might persist for years on Jupiter. Reactions that would require extreme conditions in our laboratories happen naturally in the Jovian atmosphere, driven by sunlight from above and heat from below. The Great Red Spot exists in this complex chemical soup, and its color must arise from some substance or combination of substances that absorbs blue and green light while reflecting red. The question that puzzled scientists for so long was not whether such a substance existed, but what exactly it was, and how it came to be concentrated in this one persistent storm. Over the years, many candidates were proposed. Phosphorus compounds were suggested early on, since certain phosphorus molecules can appear red under the right conditions. Sulfur was another popular candidate, capable of forming a wide range of colorful compounds depending on its chemical state. Organic molecules, complex chains of carbon and hydrogen, were also considered, since Jupiter's atmosphere contains methane and other hydrocarbons that could potentially be processed into larger, more colorful molecules by solar radiation or lightning. Each of these hypotheses had strengths and weaknesses. Each could explain some aspects of the Great Red Spot's appearance, while struggling to account for others. The challenge was not just identifying a substance that could be red, but explaining why that substance would be concentrated specifically in the Great Red Spot and not distributed more broadly across Jupiter's atmosphere. Why would phosphorus or sulfur or organic molecules accumulate in this one storm and not in others? Why would the color persist for centuries when Jupiter's atmosphere is constantly mixing and churning? The mystery was not just chemical, but dynamical, requiring an explanation that accounted for both the color itself and its localization in this particular, persistent feature. And so the Great Red Spot kept its secret, that crimson eye gazing at us across the solar system, absorbing light in ways we could observe but not fully understand. Generations of planetary scientists studied it, proposed theories, debated possibilities, and still the definitive answer remained elusive. There was something almost poetic about this, a mystery that persisted even as our technology improved, even as we sent spacecraft to Jupiter and analyzed its light with increasingly sophisticated instruments. The Great Red Spot seemed to guard its mystery jealously, yielding only partial answers, hinting at deeper truths that remain just out of reach. But that is the nature of scientific inquiry, is it not? We ask questions, we gather data, we propose explanations, and sometimes the universe answers quickly and sometimes it makes us wait. The waiting is not failure. The waiting is part of the process, the slow accumulation of knowledge that eventually reaches a tipping point where suddenly, beautifully, things begin to make sense, and that is what has happened with the Great Red Spot. After 400 years of observation, after decades of modern scientific investigation, we have finally begun to understand why this ancient storm absorbs light the way it does. The answer, as we will explore together tonight, involves the interaction of sunlight with Jupiter's upper atmosphere, the creation of specific chemical compounds through photochemical reactions, and the unique conditions that exist within the Great Red Spot itself. But before we dive into that answer, let us pause for a moment and simply appreciate the mystery itself. There is value in not knowing, in sitting with uncertainty, in allowing wonder to exist without immediately demanding resolution. The Great Red Spot has been a source of wonder for centuries, and even now that we understand more about its color, that wonder does not diminish. If anything, understanding deepens wonder, because we begin to see the intricate connections between light and chemistry and atmospheric dynamics, the elegant complexity that underlies what appears to be simply a red spot on a distant planet. So breathe slowly, let your thoughts drift among the clouds of Jupiter, and know that the mystery is part of the beauty. We are not in a hurry tonight. The Great Red Spot has waited 400 years to share its secrets, and it will wait a little longer while we appreciate the journey as much as the destination. Now let us travel backward in time, back through the centuries, to understand how humanity first came to know this distant storm, and how our understanding has evolved with each generation of observers and each advance in technology. Because the Great Red Spot is not just a scientific mystery, it is also a historical one, a feature that has been part of human awareness for longer than many nations have existed, a constant in a changing world, a reminder that some things endure beyond the brief span of human lives. The story of the Great Red Spot begins in some ways with the story of the telescope itself. Before 1609, when Galileo first turned a telescope toward the night sky, Jupiter was simply a bright wandering star, a point of light that moved against the fixed background of constellations in a pattern that had fascinated astronomers since ancient times. The very word planet comes from the Greek word for wanderer, and Jupiter was one of the 5 wandering stars known to ancient observers, along with Mercury, Venus, Mars, and Saturn. These 5, along with the Sun and Moon, gave us our 7 days of the week, gave us countless myths and astrological traditions, gave us a sense that the heavens were alive with powers and personalities beyond human understanding. But the telescope changed everything. When Galileo pointed his primitive instrument at Jupiter in January of 1610, he did not see a point of light. He saw a disk, a tiny circle that revealed Jupiter to be a world with extent, with surface features, with moons that orbited it like a miniature solar system. Those 4 moons, now called the Galilean moons in his honor, were among the most important discoveries in the history of science, because they showed definitively that not everything in the heavens orbited Earth. Here was clear evidence that other centers of motion existed, that the geocentric model of the universe was incomplete at best and wrong at worst. The moons of Jupiter helped open the door to the Copernican revolution, to the understanding that Earth is not the center of all things, but merely one world among many, orbiting one star among countless billions. Galileo's telescope was crude by modern standards, offering perhaps 20 times magnification, with significant distortion around the edges of the field of view. He could see Jupiter's moons as points of light changing position from night to night, but he could not see details on Jupiter's surface. The banded structure of Jupiter's atmosphere, the zones and belts that we now recognize as fundamental features, were beyond the reach of his instrument. And so the Great Red Spot, if it existed in 1610, remained hidden, waiting for better telescopes and more patient observers to reveal it to human eyes. The decades that followed saw steady improvements in telescope design and construction. Astronomers learned to grind lenses more precisely, to build longer telescopes that reduced optical aberrations, to mount their instruments more stably for extended observations. By the middle of the 17th century, telescopes had improved enough that careful observers could begin to see features on Jupiter's disk, to notice that the planet was not simply a uniform sphere, but a world with structure and variation. It was in this context that Giovanni Cassini made his observations. Cassini was an Italian astronomer who would later move to France and become the first director of the Paris Observatory. But in the 1660s he was working in Bologna, using the best telescopes available to study the planets. In 1665, he reported observing a permanent spot on Jupiter, a feature that remained visible over multiple observations and that appeared to rotate with the planet. His descriptions were detailed enough that many modern astronomers believe he was looking at the Great Red Spot, or at least at a precursor to the current storm. Cassini was not the only observer to notice unusual features on Jupiter during this period. Robert Hooke, the English scientist famous for his work on microscopy and the law of elasticity, also reported seeing a spot on Jupiter around the same time. Other astronomers across Europe made similar observations, contributing to a growing body of evidence that Jupiter possessed persistent atmospheric features that could be tracked and studied over time. But the observational record from this period is incomplete and sometimes contradictory. Different observers used different telescopes with different optical qualities. They observed under different atmospheric conditions, from different locations at different times. The terminology they used was not standardized, so it can be difficult to determine whether two observers describing a spot on Jupiter were looking at the same feature or at different features in similar locations. The Great Red Spot of the 17th century remains somewhat ghostly, a feature we believe was present but cannot confirm with absolute certainty. What we can say is that by the late 1600s, astronomers were aware that Jupiter's atmosphere was dynamic and structured, that features could persist for extended periods while also changing over time. They had begun the long project of mapping and monitoring Jupiter, a project that would continue through the centuries, accumulating observations that would eventually reveal the Great Red Spot as the persistent ancient storm we recognize today. The 18th century brought further improvements in telescope technology and more systematic programs of planetary observation. Astronomers began to keep more detailed records, to draw Jupiter's appearance at different times, to track the motion of features across the planet's disk. The rotation period of Jupiter was determined with increasing precision, revealing that this giant world spins remarkably quickly, completing a full rotation in just under 10 hours. This rapid rotation is part of why Jupiter appears slightly flattened at the poles and bulging at the equator, and it is part of what drives the complex atmospheric dynamics that create and maintain features like the Great Red Spot. But curiously, the observational record of the Great Red Spot becomes somewhat sparse in the late 18th and early 19th centuries. There are periods of decades where no clear observations of a prominent red spot appear in the historical record. This has led some researchers to suggest that the current Great Red Spot may not be exactly the same feature that Cassini observed, that there may have been a period when the original spot faded or disappeared, followed by the formation of a new spot in the same general region. Others argue that the gaps in the record simply reflect periods of less active observation or less favorable viewing conditions, and that the Great Red Spot has been continuously present throughout. This ambiguity is part of what makes the Great Red Spot so fascinating from a historical perspective. We cannot be absolutely certain of its age. We cannot trace an unbroken lineage of observations from Cassini to the present day. What we can say is that by the 1870s, a prominent red oval feature was clearly visible in Jupiter's southern hemisphere, and that this feature has been continuously observed and documented ever since. For at least 150 years, we have definitive, detailed records of the Great Red Spot, and for possibly 350 years or more, it has been a feature of Jupiter's face. Consider what this longevity means. The Great Red Spot has outlasted empires. It has outlasted revolutions, world wars, technological transformations that have remade human civilization multiple times over. When the American Declaration of Independence was signed, the Great Red Spot was spinning on Jupiter. When Napoleon marched across Europe, the Great Red Spot was spinning on Jupiter. When the first telegraph messages were sent, when the first airplanes flew, when the first humans walked on the moon, the Great Red Spot was spinning on Jupiter. It is a reminder that the universe operates on timescales that dwarf human history, that phenomena can persist for centuries or millennia, while human civilizations rise and fall and rise again. And throughout all this time, the Great Red Spot has been absorbing light in its distinctive way, appearing red to human eyes and human instruments, keeping its chemical secrets, while generations of scientists wondered and theorized and debated. The mystery of its color is not just a scientific puzzle, but a historical one, a question that connects us to all those observers who came before, who looked at that same red spot and wondered what could possibly cause such a persistent, vivid feature on a distant world. The 19th century brought new tools for studying planetary atmospheres, most notably the development of spectroscopy. By analyzing the light from distant objects, astronomers could begin to determine what chemical elements and compounds were present. The spectrum of light acts like a fingerprint, with different substances absorbing and emitting light at characteristic wavelengths. Early spectroscopic observations of Jupiter revealed the presence of methane and ammonia in its atmosphere, the first direct chemical detections of atmospheric composition on another planet. But spectroscopy of the Great Red Spot specifically was challenging. The spot is relatively small compared to the full disk of Jupiter, and separating its light from the light of the surrounding atmosphere requires careful observation and analysis. Early spectroscopic studies could detect that the spot appeared redder than nearby regions, but they could not definitively identify what substance was causing that redness. The fingerprint was there, but the database of known fingerprints was not complete enough to make a match. Throughout the 20th century, technology continued to advance, and our understanding of Jupiter deepened accordingly. Ground-based telescopes grew larger and more sophisticated. Spectroscopic techniques became more precise, covering wider ranges of wavelengths with greater resolution. And most significantly, the space age began, offering the possibility of studying Jupiter not just from Earth, but from spacecraft that could travel to the outer solar system and examine the giant planet up close. The first spacecraft to visit Jupiter were Pioneer 10 and Pioneer 11, which flew past in 1973 and 1974 respectively. These small, hardy probes carried instruments to study Jupiter's magnetic field, radiation environment and atmosphere, and they returned the first close-up images of the Great Red Spot. For the first time, humanity could see this ancient storm in detail, could observe the complex swirling patterns within the spot, could appreciate its true scale and structure. The images from the Pioneer missions were revolutionary, but they were just a preview of what was to come. In 1979, Voyager 1 and Voyager 2 flew past Jupiter, carrying far more sophisticated cameras and instruments. The Voyager images of the Great Red Spot remain iconic to this day, revealing a churning maelstrom of clouds with intricate patterns of light and shadow, revealing smaller storms being swept around the spot's periphery, revealing the dynamic, ever-changing nature of this ancient feature. The Voyager missions also provided more detailed spectroscopic data, helping to constrain the chemical composition of Jupiter's atmosphere and the Great Red Spot specifically. But even with this wealth of new data, the fundamental question remained unanswered. What exactly was causing the red color? What substance was absorbing blue and green light while reflecting red? The mystery persisted, deepened now by the knowledge that any explanation would need to account for the complex swirling structure revealed by close-up imaging. If you are still with me on this journey, I would love to hear from you. What have you found most interesting so far? The ancient history of the observations, the longevity of this storm that has outlasted so much of human history, or perhaps the tantalizing mystery of what creates that distinctive red color? Leave a comment below and let me know what captures your imagination. And if you have not already, please consider subscribing so that you can join us on future cosmic journeys. The next major mission to Jupiter was Galileo, which arrived in 1995 and spent 8 years studying the giant planet and its moons. Unlike the Pioneer and Voyager missions, which were brief flybys, Galileo was an orbiter, circling Jupiter dozens of times and returning data over an extended period. Galileo also carried an atmospheric probe that descended into Jupiter's clouds, providing direct measurements of temperature, pressure, and composition at different depths. The Galileo mission transformed our understanding of Jupiter in countless ways, but the mystery of the Great Red Spot's color remained stubbornly elusive. The probe did not descend into the Great Red Spot itself, and while the orbiter gathered valuable data on the spot's structure and dynamics, the chemical question remained open. Various hypotheses were refined and tested, but none could definitively explain why this particular storm appeared in this particular shade of red. Part of the challenge was that Jupiter's atmosphere is incredibly complex, with chemistry occurring at many different levels and in many different ways. Sunlight streaming down from above drives photochemical reactions in the upper atmosphere, breaking apart molecules and creating new ones. Heat rising from Jupiter's interior drives convection and mixing, bringing material from deep within the atmosphere up to higher levels. Lightning, which Voyager detected in Jupiter's clouds, could also drive chemistry, creating exotic compounds through electrical discharge. With so many possible chemical pathways, identifying the specific one responsible for the Great Red Spot's color was like finding a needle in a haystack. And then there was Juno. The Juno spacecraft arrived at Jupiter in 2016, carrying instruments specifically designed to study Jupiter's atmosphere, interior, and magnetic field in unprecedented detail. Juno's orbit was unusual, swooping in close to Jupiter's cloud tops at high latitudes and then swinging out into a large ellipse that carried it far from the planet. This orbit allowed Juno to study features like the Great Red Spot from angles and distances never before achieved, gathering data that would finally begin to unravel the 400-year-old mystery. We will return to Juno and its discoveries shortly, because the data from this remarkable mission has been central to our new understanding of why the Great Red Spot absorbs light the way it does. But for now, let us pause in this historical journey and appreciate how far we have come. From Galileo's first glimpse of Jupiter's moons through a crude telescope to the sophisticated instruments orbiting Jupiter today, humanity has maintained an unbroken thread of curiosity about this giant world and its most famous storm. That thread connects us to all who have wondered before, and it will extend forward to all who will wonder after us. The Great Red Spot has been watching us, in a sense, throughout this journey. It does not care about human history, does not concern itself with our wars and revolutions and scientific advances, but we have cared about it, generation after generation, building instruments and launching spacecraft and writing papers and theories, all to understand this distant, persistent, mysterious feature. There is something beautiful about this one-sided relationship, about the intensity of human curiosity focused on something that remains utterly indifferent to our existence. The Great Red Spot spins on, and we watch, and we wonder, and slowly, patiently, we begin to understand. Now let us consider the colour itself more closely, because to understand why the Great Red Spot appears red, we must first understand how colour works, how light interacts with matter, how our eyes and instruments perceive the wavelengths that reach them from across the vast distances of space. Light, as you may know, is a form of electromagnetic radiation, a wave of oscillating electric and magnetic fields that travels through space at the fastest speed the universe allows. What we call visible light is just a small portion of the electromagnetic spectrum, the range of wavelengths that human eyes happen to be sensitive to. This range extends from roughly 400 nanometers, which we perceive as violet, to roughly 700 nanometers, which we perceive as red. Shorter wavelengths beyond violet include ultraviolet, X-rays, and gamma rays. Longer wavelengths beyond red include infrared, microwaves, and radio waves. The visible spectrum is a tiny window in a vast continuum, but it is the window through which we see the universe. When light encounters matter, several things can happen. The light can pass through unchanged, which we call transmission. The light can bounce off, which we call reflection. Or the light can be absorbed, its energy taken up by the matter it encounters, and converted into other forms, typically heat. The colour of an object depends on which wavelengths it absorbs and which it reflects. An object appears red when it absorbs blue and green light while reflecting red light back to our eyes. An object appears blue when it absorbs red and green light while reflecting blue. And an object appears white when it reflects all visible wavelengths equally, or black when it absorbs all visible wavelengths. The Great Red Spot appears red because something in its clouds is absorbing blue and green light while reflecting red. This much has been clear from spectroscopic observations for decades. When scientists analyze the light coming from the Great Red Spot and compare it to the light coming from nearby regions of Jupiter's atmosphere, they find that the spot is relatively dark at short wavelengths, those corresponding to blue and green, and relatively bright at long wavelengths, those corresponding to red and orange. This pattern of absorption is the fingerprint we have been trying to match to a specific chemical substance. The challenge is that many different substances can produce reddish colors through many different absorption mechanisms. Red light can be reflected by compounds containing chromophores, molecular structures that absorb light at specific wavelengths due to the arrangement of their electrons. Different chromophores absorb different wavelengths depending on their precise structure. So to identify the chromophore responsible for the Great Red Spot's color, scientists needed to find a compound that matched the observed absorption spectrum precisely, not just approximately, but in detail, wavelength by wavelength. For years, the leading candidates included sulfur compounds and phosphorus compounds, both of which can form colorful molecules under the right conditions. Elemental sulfur, for instance, can exist in various forms with colors ranging from yellow to orange to red. Phosphorus compounds, particularly certain phosphorus hydrogen molecules, can also appear red. These elements are present in Jupiter's atmosphere, albeit in small amounts, so it was plausible that they might concentrate in the Great Red Spot and contribute to its colour. But there were problems with both hypotheses. The detailed absorption spectrum of the Great Red Spot did not quite match the spectra of known sulfur or phosphorus compounds. The amount of these elements required to produce the observed colour seemed inconsistent with other observations of Jupiter's atmosphere, and neither hypothesis could easily explain why the colouring agent would be concentrated specifically in the Great Red Spot rather than distributed more broadly across Jupiter's cloud system. Another class of candidates were organic compounds, complex molecules built from carbon, hydrogen, and other elements. Jupiter's atmosphere contains methane and other hydrocarbons, and when these molecules are exposed to ultraviolet light or electrical discharge, they can undergo reactions that produce larger, more complex molecules. Some of these complex organic molecules can be colourful, absorbing visible light due to extended systems of conjugated bonds within their structures. The brownish-red colour of Jupiter's belts might be due to such organic compounds, and it was reasonable to wonder if similar compounds might be concentrated in the Great Red Spot. This brings us to the breakthrough that has emerged in recent years, the discovery that has finally provided a compelling explanation for the Great Red Spot's distinctive appearance. And it turns out that the answer involves not sulfur or phosphorus directly, but rather a photochemical process occurring in the upper reaches of Jupiter's atmosphere, where sunlight breaks down simple molecules and creates new substances that absorb light in just the right way. The key insight came from laboratory experiments combined with data from the Juno spacecraft and other observations. Scientists at NASA's Jet Propulsion Laboratory and elsewhere began to carefully study what happens when ammonia and acetylene, both present in Jupiter's atmosphere, are exposed to ultraviolet light under conditions similar to those in the upper atmosphere above the Great Red Spot. What they found was fascinating and elegant. When ammonia and acetylene are irradiated with ultraviolet light, they undergo photochemical reactions that produce a reddish-brown material. The exact chemical structure of this material is complex, involving chains of carbon and nitrogen atoms in various configurations, but its optical properties, meaning the way it absorbs and reflects light, closely match the observed properties of the Great Red Spot. In laboratory experiments, the material produced by irradiating ammonia and acetylene appeared red, and when scientists measured its absorption spectrum, they found a good match to the absorption observed in the Great Red Spot. This discovery was significant for several reasons. First, it provided a mechanism for producing the red colour from substances known to be present in Jupiter's atmosphere. Ammonia is abundant in Jupiter's upper atmosphere, forming the clouds we see as the bright zones. Acetylene is produced by photochemical reactions involving methane, and it is present in the stratosphere above the clouds. Both ingredients are available, and the ultraviolet light needed to drive the reaction comes from the sun. The process is continuous, ongoing, self-sustaining, as long as sunlight reaches Jupiter's upper atmosphere. Second, the hypothesis explains why the colour is concentrated in the Great Red Spot, rather than spread evenly across Jupiter. The Great Red Spot is an unusually high feature, with clouds that rise several kilometers above the surrounding atmosphere. This means that material in the Great Red Spot is exposed to more intense ultraviolet radiation than material at lower altitudes, because there is less atmosphere above to absorb the UV before it arrives. The elevated clouds of the Great Red Spot are essentially a preferred site for photochemical production of the red chromophore. Additionally, the anticyclonic nature of the Great Red Spot may contribute to concentrating the coloured material. Anticyclones on Jupiter are associated with upwelling motion, bringing material from lower altitudes up to higher levels, where it can be processed by sunlight. The circulation within the spot may act to concentrate the photochemical products in its centre, creating the distinctive colour pattern observed. Perhaps you're wondering, if this photochemical process produces the red colour, why does the Great Red Spot sometimes appear more or less intensely coloured at different times? This is an excellent question, and the answer relates to the dynamic, ever-changing nature of Jupiter's atmosphere. The intensity of the red colour can vary depending on how much chromophore-producing material is available, how intense the ultraviolet radiation is, and how effectively the circulation within the spot concentrates the coloured products. Over the decades and centuries, the Great Red Spot's colour has fluctuated, sometimes appearing a deep brick red, sometimes a paler salmon, or even greyish colour. These variations are consistent with a photochemical origin, as changes in atmospheric conditions would naturally lead to changes in the rate of chromophore production and accumulation. The discovery that the Great Red Spot's colour arises from photochemistry in the upper atmosphere resolves a mystery that has persisted for centuries, but it also opens new questions, new avenues for investigation, new reasons to study Jupiter and its remarkable atmosphere. How exactly does the circulation within the Great Red Spot work to concentrate the coloured material? Are similar processes occurring on other giant planets, perhaps contributing to the colours observed in Saturn's atmosphere or even on distant exoplanets? What can we learn about atmospheric chemistry more generally from studying these processes on Jupiter? These questions will occupy planetary scientists for years to come, and the Great Red Spot will continue to be a focus of study and wonder. But for tonight, let us rest in the satisfaction of having solved at least part of the puzzle. We now understand, in broad terms, why this ancient storm absorbs light the way it does. Sunlight, ammonia, acetylene, and 400 years of continuous chemistry have painted this crimson eye on Jupiter's face. Consider the elegance of this answer, the way it connects distant phenomena through chains of cause and effect. The Sun, that fusion reactor 93 million miles from Earth and roughly 500 million miles from Jupiter, sends photons streaming outward through the solar system. Some of those photons reach Jupiter's upper atmosphere, where they encounter molecules of ammonia that rose from deeper layers, and molecules of acetylene produced by earlier photochemical reactions. The ultraviolet photons break chemical bonds, set atoms in motion, create new compounds with extended structures of carbon and nitrogen. These new compounds absorb blue and green light while reflecting red, and that red light continues its journey outward, across hundreds of millions of miles of space, eventually reaching telescopes on Earth or instruments on spacecraft, where we detect it and wonder about its origin. This chain of events, from nuclear fusion in the Sun to colour perception in human eyes, spans enormous distances and involves countless individual interactions, yet it produces a result we can see and study and understand. The Great Red Spot appears red because the universe has certain rules, certain regularities, certain patterns of cause and effect that operate the same way whether we are there to observe them or not. Our understanding is a kind of participation in these patterns, a way of joining the cosmic dance even from our small distant position. If you're still here, still listening, still drifting with me through the clouds of Jupiter, I'm curious what has captured your attention so far. Has it been the ancient history of observations, the persistence of this storm across centuries of human history? Has it been the chemistry, the elegant dance of molecules and photons that produces the colour we see? Has it been the sense of scale, the vastness of Jupiter and its storm compared to our small Earth? Leave a comment below and share your thoughts. And as we continue this journey together, feel free to close your eyes if you wish, to let the words carry you deeper into relaxation, deeper into the gentle embrace of sleep. Now let us consider what happens to light as it journeys to Jupiter and encounters this ancient storm. Light from the Sun travels outward through space, a continuous stream of photons across the entire electromagnetic spectrum. By the time this light reaches Jupiter, it has travelled for about 43 minutes, covering a distance of roughly 500 million miles. The intensity of the light is much reduced compared to what we experience on Earth, since Jupiter is roughly 5 times farther from the Sun than we are, and light intensity decreases with the square of the distance. If you stood on Jupiter's cloud tops, the Sun would appear as a smaller, dimmer disk than we see from Earth, providing only about 4% as much energy. But 4% of the Sun's energy is still an enormous amount. Even at Jupiter's distance, sunlight is powerful enough to drive chemistry, to warm the atmosphere, to create the photochemical reactions that colour the Great Red Spot. The ultraviolet portion of this light, though invisible to human eyes, carries enough energy to break chemical bonds, to dissociate molecules, to set in motion the cascades of reactions that produce the chromophores responsible for the spot's distinctive hue. When sunlight enters Jupiter's atmosphere, it encounters a complex layered structure of clouds and hazes. The uppermost visible clouds are composed of ammonia ice crystals, forming at altitudes where the temperature is cold enough for ammonia to condense from a gas to a solid. These ammonia clouds appear white or pale in color, reflecting sunlight efficiently across all visible wavelengths. They form the bright zones we see banding Jupiter's disk. Below the ammonia clouds lie deeper layers that we cannot see directly. There are clouds of ammonium hydrosulfide, a compound formed from ammonia and hydrogen sulfide, existing at levels where the temperature and pressure are suitable for its condensation. Below these are water clouds, deep in Jupiter's atmosphere where pressures are many times that of Earth's surface, and below even the water clouds the distinction between atmosphere and planet becomes meaningless, as hydrogen gradually transitions from a gas to a liquid and eventually to a metallic fluid at enormous pressures. The Great Red Spot extends upward from these deep layers, its clouds rising several kilometers above the surrounding atmosphere. This elevation is crucial to understanding both its persistence and its color. Because the spot is higher, it is more exposed to direct sunlight, including the ultraviolet radiation that drives photochemistry. And because it is a high-pressure system, with air circulating outward at its top, it tends to accumulate material rather than disperse it. Within the Great Red Spot, the photochemical process occurs primarily in the upper layers, where ultraviolet light can penetrate, and where ammonia and acetylene are both available. The products of these reactions, the chromophore molecules responsible for the red color, form a kind of haze or coating on the upper cloud particles. This chromophore layer is relatively thin, concentrated in the top 10 to 20 kilometers of the spot's atmosphere, but it is enough to significantly alter the light that reaches our eyes and instruments. When white sunlight strikes the Great Red Spot, several things happen. Some of the light is reflected directly by the ammonia cloud particles, bouncing back into space without being significantly absorbed. Some of the light penetrates deeper into the atmosphere, where it may be absorbed by other substances or scattered by other particles, and some of the light interacts with the chromophore layer, where blue and green wavelengths are preferentially absorbed while red wavelengths pass through more freely or are reflected. The net result of all these interactions is that the light reflected from the Great Red Spot is depleted in blue and green wavelengths and enriched in red wavelengths. When we observe the spot through a telescope or analyze its light with a spectrometer, we see this characteristic signature. The absorption that has puzzled scientists for so long, and that we now understand to be the result of photochemical processing in Jupiter's upper atmosphere. It is worth pausing to appreciate how remarkable it is that we can learn so much about a distant world simply by analyzing the light it reflects. The photons that left the Sun 43 minutes earlier, that traveled 500 million miles through space, that interacted with Jupiter's clouds and chromophores and began the journey back toward Earth. These photons carry information encoded in their wavelengths and intensities. By carefully measuring this information, by comparing it to the results of laboratory experiments and theoretical models, we can deduce what is happening in an atmosphere we have never directly touched, on a planet we have never visited in person. This is the power of remote sensing, the ability to learn about distant objects without physically traveling to them. It is how we have explored most of the universe, how we know about the compositions of stars billions of light years away, how we have detected the atmospheres of planets orbiting other suns. The Great Red Spot is just one example of this remarkable capability. One case where patience and ingenuity have allowed us to solve a centuries-old mystery from a distance of hundreds of millions of miles. And yet, for all that we have learned, there is so much we still do not know. The exact chemical structure of the chromophores in the Great Red Spot remains uncertain. We know they are produced from ammonia and acetylene. We know they absorb blue light and reflect red. But the precise molecular formulas, the detailed arrangements of atoms, are still being investigated. The processes occurring deep within the Great Red Spot, below the cloud tops we can observe, are still largely mysterious. The internal heat flow, the deep circulation patterns, the way the spot maintains its coherence against the constant churning of Jupiter's atmosphere, these are active areas of research, questions that future observations and missions will help to answer. Perhaps you find it comforting that mysteries remain. Perhaps you appreciate that even after 400 years, even with all our advanced technology, there are still secrets to uncover, still questions to ask, still wonders to discover. The universe is not a puzzle to be solved once and then forgotten. It is an endless source of curiosity, a companion that rewards our attention with ever deeper levels of understanding and ever more beautiful questions. As we continue our exploration tonight, let us carry with us this sense of open wonder. The Great Red Spot has yielded some of its secrets, but it has not yielded all of them. And that is as it should be. The journey of understanding is never complete, the horizon always receding as we approach, always revealing new territories to explore. Tonight, we rest in the knowledge we have gained while remaining curious about the knowledge still to come. Now, let us turn our attention to the spacecraft that have made our understanding possible, the robotic emissaries we have sent across the vast distances of space to study Jupiter and its remarkable atmosphere. These missions represent some of humanity's greatest achievements, feats of engineering and determination that have extended our senses across hundreds of millions of miles and brought the outer solar system within our reach. The first spacecraft to venture toward Jupiter were Pioneer 10 and Pioneer 11, launched in 1972 and 1973 respectively. These were modest spacecraft by today's standards, weighing only a few hundred kilograms and carrying a limited suite of instruments. But they were pioneers in the truest sense, blazing a trail through the asteroid belt and into the outer solar system that no human-made object had traveled before. Pioneer 10 reached Jupiter in December of 1973, passing within about 80,000 miles of the planet's cloud tops. The images it returned were blurry by later standards, but they showed the Great Red Spot in more detail than any ground-based telescope could achieve. For the first time, we could see the spot as a three-dimensional structure, with hints of the complex swirling patterns within. Pioneer 10 also measured Jupiter's intense radiation belts, which posed significant challenges for later missions, and it detected the planet's powerful magnetic field far stronger than Earth's. Pioneer 11 followed a year later, passing Jupiter in December of 1974 on its way to Saturn. It flew closer to Jupiter than Pioneer 10 had, approaching within about 26,000 miles of the cloud tops, and it returned additional images and data that complemented what Pioneer 10 had gathered. Together, the two Pioneer missions demonstrated that spacecraft could survive the journey to Jupiter and return valuable scientific data, paving the way for the more ambitious missions that would follow. Those more ambitious missions were Voyager 1 and Voyager 2. Launched in 1977 and still operating in interstellar space today, the Voyager spacecraft were larger and more capable than the Pioneers, carrying 11 scientific instruments each, including cameras capable of returning high-resolution images in multiple wavelengths. When Voyager 1 flew past Jupiter in March of 1979, followed by Voyager 2 in July, they transformed our understanding of the giant planet and its system of moons. The Voyager images of the Great Red Spot are among the most iconic in the history of planetary exploration. They revealed the spot as a vast anticyclone, with clouds swirling counterclockwise around a relatively calm central region. They showed smaller storms being caught in the spot's circulation and swept around its periphery. They captured the subtle gradations of color within the spot, from deep red in certain regions to paler shades in others. For the first time, we could see the Great Red Spot as a dynamic, evolving feature, not just a static marking on Jupiter's face. The Voyager missions also provided spectroscopic data that helped constrain the composition of Jupiter's atmosphere. By analyzing the light reflected from different regions, including the Great Red Spot, scientists could estimate the abundances of various atmospheric constituents and begin to understand the chemistry occurring at different altitudes. But even with Voyager's advanced instruments, the mystery of the spot's color remained unsolved. The data were consistent with several possible explanations, and no single hypothesis could be definitively confirmed. After Voyager, the next major mission to Jupiter was Galileo, which arrived in December of 1995 after a 6-year journey from Earth. Unlike the Pioneer and Voyager missions, which were brief flybys, Galileo was an orbiter, designed to spend years studying Jupiter and its moons in detail. It also carried an atmospheric probe that would descend into Jupiter's clouds, providing direct measurements of conditions at depth. Galileo's orbital mission lasted until 2003, when the spacecraft was deliberately crashed into Jupiter to prevent any possibility of contaminating the moon Europa, which was suspected of harboring a subsurface ocean. Over those 8 years, Galileo made dozens of orbits around Jupiter, studying the Great Red Spot and other atmospheric features from multiple angles and at multiple times. The spacecraft observed changes in the spot's appearance over years, tracking the slow evolution of its size, shape, and color. The atmospheric probe released from Galileo in July of 1995 entered Jupiter's atmosphere 5 months later and transmitted data for about an hour before being destroyed by the increasing temperature and pressure at depth. Unfortunately, the probe did not descend through the Great Red Spot itself, entering the atmosphere in a relatively clear region far from the famous storm. The data it returned were valuable for understanding Jupiter's general atmospheric composition, but they did not directly address the mystery of the spot's color. Still, Galileo's observations of the Great Red Spot from orbit contributed important information. The spacecraft's near-infrared mapping spectrometer revealed details of the spot's vertical structure, showing that it extended deep into Jupiter's atmosphere and that its upper layers were elevated above the surrounding clouds. Galileo's images showed the ongoing dynamics within the spot, the constant churning and swirling that maintains its coherence against the shearing forces of Jupiter's atmosphere. And then there is Juno, the most recent and in many ways the most capable spacecraft to study Jupiter. Juno arrived in July of 2016, entering a highly elliptical orbit that carries it close to Jupiter's cloud tops at Perigove, the point of closest approach, and then swings it far out into space. This unusual orbit allows Juno to study Jupiter's polar regions, which are difficult to observe from Earth, and to pass close enough to the cloud tops to study atmospheric features in unprecedented detail. Juno carries a suite of instruments designed specifically to address fundamental questions about Jupiter's origin, interior structure, and atmosphere. Its microwave radiometer can peer deep into Jupiter's clouds, sensing thermal emission from layers far below the visible surface. Its visible and infrared cameras have captured stunning images of the Great Red Spot and other atmospheric features. Its ultraviolet spectrograph has studied the auroras that dance around Jupiter's poles, revealing the complex interactions between the planet's atmosphere and its powerful magnetic field. The data from Juno have been crucial in confirming the photochemical explanation for the Great Red Spot's color. By measuring the distribution of ammonia and other compounds in the upper atmosphere, Juno has helped constrain the models of photochemical production of chromophores. By imaging the spot at multiple wavelengths and from multiple angles, Juno has revealed details of its structure that support the idea of a thin chromophore layer concentrated in the uppermost clouds. Juno has also observed something poignant about the Great Red Spot. It is shrinking. Measurements over the past century have shown that the spot's width has decreased significantly, from about 40,000 kilometers in the late 1800s to about 16,000 kilometers today. The spot that was once 3 Earths wide is now barely 1 Earth wide. This shrinkage has accelerated in recent decades, leading some scientists to wonder whether the Great Red Spot might eventually disappear altogether. We will explore this possibility later in our journey, but for now, let us simply note that the Great Red Spot, ancient and persistent as it seems, is not eternal. It is a dynamic feature of a dynamic atmosphere, subject to forces and processes that may eventually cause it to weaken and dissipate. This does not diminish its wonder. If anything, it deepens it. We are privileged to live in a time when this ancient storm is still visible, still studiable, still revealing its secrets to our patient inquiry. If you are still with me on this cosmic journey, I would love to know what has captured your imagination so far. Perhaps it is the idea of spacecraft traveling for years across the vast darkness to reach Jupiter. Perhaps it is the detailed images they have returned, bringing the Great Red Spot into sharp focus for the first time. Perhaps it is the bittersweet knowledge that this ancient storm is slowly changing, that the feature our descendants might see will be different from the one we observe today. Leave a comment below and share your thoughts, and let us continue together into the deeper mysteries of Jupiter's crimson eye. The missions we have discussed, Pioneer, Voyager, Galileo, and Juno, represent decades of exploration, countless hours of human effort, billions of dollars of investment, and yet, in a sense, they are just the beginning. Future missions are being planned that will study Jupiter in even greater detail, that will explore its moons and perhaps even send probes deep into its atmosphere. The Europa Clipper mission, launched recently, will study the icy moon Europa and its suspected subsurface ocean, a world that might harbour conditions suitable for life. Future concepts include landers for Europa, atmospheric probes for Jupiter, and even missions that would sail on the methane seas of Saturn's moon Titan. The exploration of the outer solar system is an ongoing endeavour, a multi-generational project that will occupy humanity for centuries to come. The Great Red Spot is just one target among many, one mystery among countless mysteries waiting to be explored. But it holds a special place in our imagination, a symbol of the strange and beautiful worlds that exist beyond our small blue planet, a reminder that the universe is vast and wonderful and worth the effort of understanding. As we rest with these thoughts, let us appreciate the chain of curiosity and effort that connects us to the earliest observers of Jupiter. Galileo, pointing his small telescope at a bright wandering star and seeing moons for the first time. Cassini, noting a permanent spot and wondering what it might be. The countless astronomers who tracked and sketched and photographed Jupiter over the centuries. The engineers who built spacecraft capable of surviving the journey to the outer planets. The scientists who analyzed the data and slowly, patiently, pieced together an understanding of why the Great Red Spot absorbs light the way it does. We are part of this chain, you and I. By wondering about the Great Red Spot, by seeking to understand it, we join the community of curious minds that stretches back through history and forward into the future. Our curiosity is a kind of light, illuminating the darkness of ignorance, revealing the beautiful structures hidden in the cosmos. And like the light that reflects from Jupiter's clouds and travels across space to reach our eyes, our curiosity connects us to distant worlds, makes them part of our experience, transforms them from abstract points of light into places we can know and wonder about. So let us continue our journey together, drifting among the clouds of Jupiter, exploring the chemistry of color and the physics of storms, contemplating what it means to understand something so distant and so ancient. The night is long, and there is much more to discover, but for now rest in the gentle wonder of knowing that a 400-year mystery has finally yielded its secrets, that the crimson eye of Jupiter gazes at us across the darkness, and that we, small and brief as we are, have found a way to gaze back and understand. The photons that left the Sun 43 minutes ago, that touched the chromophore layer of the Great Red Spot, that began the long journey back toward Earth, are arriving now at telescopes around the world. Astronomers are gathering this light, analysing its wavelengths, adding new data to the long record of observations that stretches back centuries. Somewhere, a graduate student is writing a thesis about the atmospheric dynamics of Jupiter. Somewhere, a child is looking through a backyard telescope and seeing the Great Red Spot for the first time, wondering what that strange marking might be. The chain of curiosity continues, each link connected to all the others, stretching backward and forward through time, and we are here, in this quiet moment, contemplating the vastness and the beauty, and the slow unravelling of cosmic mysteries. The Great Red Spot spins on, indifferent to our attention but transformed by it nonetheless, now understood in ways it has never been understood before. The universe does not care about our understanding, but our understanding is a kind of gift we give to ourselves, a way of participating in the cosmic dance, a light that we kindle in the darkness. Let these thoughts carry you deeper into relaxation, deeper into the gentle embrace of sleep. The mysteries of Jupiter will be there when you wake, waiting to be explored further. But for now, rest in the knowledge we have shared, the wonder we have kindled, the connection we have made across the vast distances of space and time. The Great Red Spot watches, and we watch back, and in that mutual gaze there is something profound and beautiful and worth cherishing. And the journey continues, the storm keeps spinning, the light keeps travelling, and somewhere in the depths of Jupiter's atmosphere, ammonia and acetylene are dancing with photons, creating the colours that have puzzled and delighted humanity for 400 years. The answer, when it came, was elegant and unexpected, a testament to the power of patient inquiry and the beauty of the natural world. We understand now why Jupiter's Great Red Spot absorbs light the way it does, and that understanding is a gift, a thread connecting us to the cosmos, a light in the darkness of not knowing. Rest now, as the Great Red Spot rests in its ancient spinning, as Jupiter rests in its orbit around the Sun, as the Sun rests in its journey around the galaxy. We are all part of this vast, beautiful, interconnected universe, and understanding any piece of it is a way of understanding ourselves. The mystery has been solved, but the wonder remains, eternal and unchanging, a companion for all our nights and all our dreams. The chemistry that paints Jupiter's great red spot in shades of crimson is not a simple process, not a single reaction occurring once and producing a permanent result. It is an ongoing symphony of molecular transformation, a continuous dance between light and matter that has been playing out for centuries, perhaps for millennia, in the upper reaches of Jupiter's turbulent atmosphere. To truly appreciate why this ancient storm absorbs light the way it does, we must descend into the realm of molecules and photons, into the invisible world where the colors we see are born from interactions too small for any eye to witness directly. Imagine yourself floating in the upper atmosphere of Jupiter, somewhere above the Great Red Spot, in a region where the air is thin by Jovian standards, but still far denser than anything we would call atmosphere on Earth. The temperature here is cold, perhaps around 130 Kelvin, roughly negative 140 degrees Celsius. The pressure is low, similar to what you might find at the top of Earth's stratosphere, and streaming down from above, filtered through layers of haze and gas, comes sunlight. The same sunlight that warms our faces on Earth, though here it is fainter, colder, having travelled so much farther to reach this distant world. This sunlight contains a full spectrum of wavelengths, from long infrared waves that carry heat to short ultraviolet waves that carry enough energy to break chemical bonds. The visible light, the light we see with our eyes, lies in between, a narrow band of wavelengths that happens to be what our particular biology evolved to detect. But it is the ultraviolet light that concerns us most in understanding the Great Red Spot's color, because ultraviolet photons are the agents of transformation, the catalysts that drive the photochemical reactions responsible for creating the chromophores that give the spot its distinctive hue. When an ultraviolet photon encounters a molecule of ammonia floating in Jupiter's upper atmosphere, something remarkable can happen. The photon's energy is absorbed by the molecule, exciting its electrons to higher energy states. If the photon carries enough energy, it can break the chemical bonds that hold the ammonia molecule together, splitting it into fragments. Ammonia, with its chemical formula NH3, can be broken into an NH2 radical and a hydrogen atom, or into NH and two hydrogen atoms, depending on the energy of the photon and the precise dynamics of the interaction. These molecular fragments are highly reactive, eager to form new bonds with whatever other molecules they encounter. Similarly, acetylene molecules floating in the same region can be broken apart by ultraviolet light. Acetylene, with its formula C2H2, consists of two carbon atoms triple bonded together, with a hydrogen atom attached to each carbon. When ultraviolet photons strike acetylene, they can break this molecule into various fragments, including C2H radicals and hydrogen atoms. Like the fragments of ammonia, these acetylene fragments are reactive and ready to combine with other molecules in their vicinity. Now here is where the magic happens, where the colorless ingredients are transformed into something vibrant and visible. When fragments of ammonia and fragments of acetylene encounter each other in Jupiter's upper atmosphere, they can combine to form new molecules, larger and more complex than either parent compound. These new molecules contain both carbon and nitrogen atoms, linked together in chains and rings that did not exist moments before. The specific structures that form depend on the concentrations of the various fragments, the temperature and pressure of the surrounding atmosphere, and the random chance of which fragments happen to collide with which others. Among the products of these reactions are molecules with extended systems of conjugated bonds, alternating single and double bonds that allow electrons to be delocalized across the entire molecular structure. These conjugated systems are the key to understanding color, because they absorb light at specific wavelengths, determined by the length and arrangement of the conjugated chain. Short conjugated systems absorb ultraviolet light, which is why they remain invisible to our eyes. But as the conjugated system grows longer, the wavelength of maximum absorption shifts toward longer wavelengths, moving from ultraviolet into violet, then blue, then green, and eventually into the visible spectrum. The chromophores produced in Jupiter's upper atmosphere have conjugated systems just long enough to absorb blue and green light, while remaining transparent to red light. This is the molecular explanation for the Great Red Spot's color. The chromophore molecules absorb the shorter wavelengths, preventing them from being reflected back to our eyes, while the longer wavelengths pass through or bounce off the cloud particles below, traveling back across space to be detected by our telescopes and cameras. The red we see is not a color added to the light, but rather the color that remains after other colors have been subtracted. This subtractive process is similar to how paints and dyes work on Earth. When you mix yellow and blue paint to make green, you are not adding wavelengths together. Instead, the yellow pigment absorbs blue wavelengths while reflecting yellow and green, and the blue pigment absorbs red and yellow wavelengths while reflecting blue and green. The only wavelengths reflected by both pigments are the green ones, so green is what you see. Similarly, the chromophores in the Great Red Spot absorb blue and green wavelengths, leaving red as the dominant color in the reflected light. The elegance of this explanation lies in its simplicity and its consistency with what we know about Jupiter's atmosphere. Ammonia is abundant in Jupiter's upper atmosphere, rising from deeper layers where it exists as a gas and condensing into ice crystals at higher, colder altitudes. Acetylene is produced by photochemical reactions involving methane, another compound present throughout Jupiter's atmosphere. Both ingredients are available in the quantities needed to sustain the chromophore production, and the ultraviolet light from the sun provides the energy to drive the reactions. Everything fits together like pieces of a puzzle, each element necessary, each element present. But the story does not end with the production of chromophores. These molecules, once formed, do not simply float in place forever. Jupiter's atmosphere is dynamic, constantly mixing and churning, with winds that can exceed hundreds of kilometers per hour and vertical motions that carry material up and down through the cloud layers. The chromophores produced in the upper atmosphere are subject to these motions, being transported horizontally by winds and vertically by convection and diffusion. In most regions of Jupiter's atmosphere, this mixing would disperse the chromophores, spreading them out until their concentration became too low to produce a visible color. This is why most of Jupiter appears in shades of white and tan rather than deep red. The chromophores are present everywhere that sunlight reaches, and ammonia and acetylene are available, but they are diluted by mixing, their color contribution washed out by the overwhelming whiteness of the ammonia clouds below. The Great Red Spot is different. Its unique dynamics concentrate the chromophores rather than dispersing them. As an anticyclonic storm, the Great Red Spot has a circulation pattern that draws material inward at lower altitudes and pushes it outward at higher altitudes. This circulation creates a kind of trap for the chromophores produced in the upper atmosphere. Instead of being dispersed by horizontal winds, they are concentrated in the center of the spot, accumulating over time until their density is high enough to produce the deep red color we observe. Additionally, the Great Red Spot's elevated cloud tops mean that photochemical production of chromophores is enhanced compared to surrounding regions. More ultraviolet light reaches the upper levels of the spot because there is less atmosphere above to absorb it. More ammonia is available because the spot's upwelling circulation brings fresh material from below. More acetylene is present because the same photochemical processes that produce chromophores also produce this compound as an intermediate product. The Great Red Spot is a favored location for chromophore production and a trap for chromophore accumulation, and these two factors combine to produce the intense coloration that has fascinated observers for centuries. Consider for a moment the timescales involved. The photochemical reactions that produce chromophores occur continuously, driven by sunlight that arrives every moment of every Jovian day. The circulation that concentrates these chromophores operates on timescales of weeks to months, slowly accumulating colored material in the spot's center. The spot itself has persisted for centuries, maintaining its general structure even as its size and intensity have varied. This means that the red color we see today is the result of processes that have been operating for hundreds of years, layer upon layer of chromophore production and accumulation, building up the distinctive hue that marks Jupiter's most famous feature. And yet the color is not static. Observations over the past century have shown that the Great Red Spot's color varies over time, sometimes appearing a deep brick red, sometimes a paler salmon, or even grayish color. These variations reflect changes in the rate of chromophore production, the efficiency of the concentration mechanism, or both. When the spot's circulation is stronger, it may trap more chromophores and appear more intensely colored. When the circulation weakens or when atmospheric conditions reduce the rate of photochemical production, the color may fade. Some researchers have noted correlations between the Great Red Spot's color and other aspects of its appearance and behavior. When the spot is shrinking rapidly, as it has been in recent decades, the color sometimes changes as well, perhaps because the changing circulation affects the chromophore concentration. When the spot interacts with other atmospheric features, absorbing smaller storms or being distorted by jet streams, its color may temporarily intensify or fade. These correlations are still being studied, and they offer clues about the complex dynamics that govern this ancient storm. If you're still here with me, drifting among the molecules and photons of Jupiter's upper atmosphere, I'm curious what aspect of this chemistry has captured your attention. Is it the elegance of the explanation? The way simple ingredients combine to produce something beautiful and unexpected? Is it the timescales, the patient accumulation of color over centuries of continuous chemistry? Is it the dynamic nature of the process, the way the color varies and shifts with the ever-changing conditions of Jupiter's atmosphere? Leave a comment below and share what you find most fascinating, and let us continue together into the deeper mysteries of this crimson eye.